So I've made previous videos on equatorial mounts and the Equinox, but this video is going to combine the two and just show you how the equatorial mount would be used to track the sun from various locations on Earth during the equinox. Now, I just want to cover off on some points because my previous videos, they attract a lot of comments and there's a lot of misconceptions, a lot of misunderstandings, so hopefully we can avoid a repeat of that this time. Firstly, I acknowledge that this video alone is not proving the concept. It's demonstrating a concept. It is not proving it in this video because I'm doing the demonstrations indoors. I'm not actually tracking the sun from these different locations. So you don't need to come to this channel and say it's not proof. I'm simply showing you a concept, which is point two. I made this video to show genuine truth seekers one way they can prove to themselves the Earth cannot be flat. The geometry of the equinox does not work on a flat Earth. A lot of people come to my channel and say, yes, it does work on a flat Earth. No, it doesn't. It cannot work on a flat Earth. I'll get to that later. Number 4, equatorial mounts do not work on a flat Earth. Again, plenty of comments from flat earthers who clearly do not understand the geometry, claiming they work on a flat Earth. No, they don't. They cannot work on a flat Earth. Number 5, if the sun was doing circles above a flat Earth, you could not track it with a single axis of motion. The whole basis of how these equatorial mounts work is to track the sun by rotating a single axis that is aligned with the rotational axis of the Earth. They simply cannot work on a flat Earth if the sun was doing circles above the flat surface. There's only one position it would work, and that is at the North Pole. It could not work anywhere else. There's no point claiming that it could, because it could not. Number 6, this is one I see regularly. They claim that the telescope is programmed. Okay, well, yes, it does have programming to know where the stars are, but that is quite irrelevant to the demonstration, because the demonstration is that they can be tracked using a single axis of rotation. And in this video, I deliberately switched away from a computer equatorial mount to a simple motor drive unit, which has no programming. So there's no point claiming the telescope is programmed, because this demonstration is done with a mount that has no programming and no computer. And the big point here, if you disagree with any of my claims, if you think the equatorial mount can work on a flat Earth, if you believe the equinox can work on a flat Earth, then prove it with a working model. I'm not interested in CGI. You need to prove it with a working model using a physical light source, a flat surface, and demonstrate to me how the equatorial mounts can work from any location, being aligned based on the latitude and the direction of north, and how they can follow that moving sun that is doing circles above a flat Earth, how they can follow it using a single axis of rotation. It is simply impossible. Don't claim that it can be done until you show me a working model. And finally, the key point to this video is that on the equinox, the declination angle of the sun is 0. Now that's important because that is key to understanding the motion of these equatorial mounts on the equinox from various positions on the Earth. And if you want to research that yourself, I'll put this link in the comments, and that is if we look at the equinox, this statement down here, because the sun is on the celestial equator at the equinoxes, its declination is of course 0, and you'll hear me mentioning that declination being 0 in the video, and this is simply and easily verified. In fact, you can go to any of the Stellarium or planetarium programs. This is Sky Safari Pro, and you put in the date of the equinox and look at the actual position of the sun. There you can see the declination is 0, just over here. So on with the video. So these are the two German equatorial mounts that you saw in my previous telescope video. The one on the right is a Celestron AVX mount. The one on the left is a Skywatcher AZ-EQ6 GT. Now since that last video, I have upgraded the optical tubes on both mounts. The one on the right is now holding a Skywatcher ED80 refractor. Now this is an excellent telescope for astrophotography. You can connect a digital SLR camera to the back or even a CCD camera, and that's something I plan to get into the future. The one on the left previously had this 6-inch Schmidt-Cassegrain telescope, but I have since upgraded it to a much larger tube. This is a Celestron 9.25, and this is just superb for optical viewing of the planets and the moon, and I've got 2-inch eyepieces on it, so it's just very, very comfortable to look at the objects through that viewfinder. So what we're going to do is just have a look at the geometry once again of the Equatorial Mount, and then we'll get into how they specifically relate to the motion of the sun on the equinox from different parts of the Earth. So the key to understanding how these German equatorial mounts work is the polar alignment of this axis here. Now what that means is the axis is aligned perfectly north and south with true north and true south. Magnetic directions are irrelevant. It's aligned with the geographic north and south, and also elevated. This angle here from the horizontal represents exactly the same angle as the latitude of my location in Sydney. Now this is critical to these mounts operating correctly. This angle of elevation must match your exact latitude. So if I was at 45 south latitude, that would be a 45-degree angle. If I was on the equator, 0 latitude, it would actually be completely horizontal. And that's the key to how these German equatorial mounts work. And looking at the Skywatcher mount, that axis that we have aligned, that we polar align, looks like that. And again, the mount is aligned geographically north and south, and then elevated to match your precise latitude. Now on the side of this mount, you've got a small graduated scale there, so you can set it approximately right. We're at 34 degrees south latitude here in Sydney, and you can set it approximately 34 degrees. But the accuracy of these telescope mounts depends on them being precisely polar aligned. So if you have just 1 degree of error in the elevation, it is not going to track the object perfectly in the eyepiece. As the star or the sun moves across the sky, it's going to drift out of the eyepiece if we're just rotating that single axis. So polar alignment is critical. Once it is aligned perfectly, then we are able to track objects in the sky, the sun or the stars, by rotating one axis only, and we'll look at that now. So the mount is now powered up, and it's set up for Sydney, Australia on today's date, and I've set it for 11 AM. Now presently the mount is in what is called the home position, which means it is facing directly south and elevated at the angle where it will face the south celestial pole. So that's what we can see here in Sydney, Australia. If we were in the northern hemisphere, it would be facing the north celestial pole in the home position. Now this mount can rotate in right ascension and also in declination, and we're going to look at the declination axis in more detail because that is quite critical when it comes to understanding the motion of the sun on the equinox. You can see this scale and the small marker arrow there. You'll see that it's showing 90 degrees. So it's currently at 90 degrees declination. Now the computerized mount can show us that in the window. So the declination there is minus 90 degrees. And if we scroll through and have a look at the altitude is 33.3640, which is matching the latitude, and the azimuth is 180. So that's confirming that it is facing directly south. Let's take a look at what happens when we ask this mount to look at the sun. So we're now going to ask the mount to point towards the sun, and I realize we're indoors. It's not actually pointing at the sun. This is simply a demonstration of how the mount works. Now, during the initial acquisition of the sun, you will see the mount adjusting 2 axes. It's adjusting in right ascension and declination. Once it is facing the sun, to continue tracking the sun, the declination does not change. There are two axes here, and if we have a look at both axes, you can see at the moment neither of them are moving because the mount is in the home position. After we face the sun, you will see that one of these axes is still stationary and the other one is continually moving, and that's the tracking using the single axis of motion that I'm always talking about. So let's have a look at identifying the sun, finding the sun. There's Mercury, there's the sun. Let's ask the mount to point towards the sun. And there it goes. Now you can see it is adjusting two axes. If we were outdoors, the telescope would now be pointing towards the sun. Now you can see that if we go to show position and look at the two axes, the top one, axis 1, is not changing at all. Axis 2 is continually changing. So that is the tracking of the sun using the single axis of rotation. Now the declination of the sun on the 28th of November today is minus 21 degrees 20 minutes, and you can see that on the physical scale as well. Now this is critical when we come to look at the equinox shortly, because on the equinox, because the sun is traveling over the equator, the declination is going to be 0. So at this point the telescope mount is tracking the sun. The declination is not changing. It is tracking by rotating this polar axis only. So if we were to move that manually, that's the single axis of rotation that allows us to track the sun. Now let me just reconfigure this mount for the day of the equinox, and you'll see very clearly that the declination will be 0. So the mount is now powered down and it's parked in the home position. What I'm going to do is power on and initialize it on the 23rd of September 2017, which is the day of the equinox, and then we're going to ask it to point towards the sun, and you will see that it will have a declination of 0. So turning on, it's initializing. We're in EQ mode. Start from park, yes. Now we need to set the date to the 9th, 23rd, enter, and let's just say 11 AM, enter. And no, we don't have daylight saving at that time of the year. So enter. Okay, what we're going to do now is go to the sun. And as we saw before, the mount is slewing two axes for the initial acquisition of the position of the sun. And because the mount now thinks it is the day of the equinox, where the sun is directly above the equator, it's going to show a declination of 0. And that's exactly what we were expecting, and that is critical to the next part of the demonstration. So I've turned off the power and disconnected the handset and the power cable, and I've disengaged the clutch for right ascension, which means I can just rotate the mount by hand. Now the declination axis is still showing 0, but if I were to just move this mount by hand, you can see that it is only rotating on one axis, and that motion that the telescope is following is the actual path of the sun on the equinox from this latitude. Now, from any location on Earth on the equinox, the declination of the sun is going to be 0. Now, this mount is set up for 34 south latitude in Australia, but if we were in different latitudes, if we were in the equator or if we were at 45 north or south latitude, the angle would be different, and that's the next part of the demonstration that we're going to look at. Now, for the next part of the demonstration, I've switched to this Star Adventurer equatorial mount, which is only motorized in one axis. Now, normally I would use this bracket, and it has a manual declination adjustment just via that knob. But since we are demonstrating the equinox, and during the equinox the position of the sun is at 0 declination, we don't even need that bracket. I can bolt the telescope directly to the mount and just rotate it in RA. So at the moment it's set up for approximately 34 degrees, which is what we would have in Sydney. And I'm going to show you demonstrations for different latitudes around the world, and we're going to see that regardless of the latitude, the position of the telescope pointing at the sun will be 090 degrees when it rises, 270 degrees when it sets, and the angle at local noon when the sun is at the highest position in the sky will match 90 degrees minus the latitude. So the first demonstration will be using 34 degrees south latitude. Now, this small tracking mount in solar mode will rotate 360 degrees in 24 hours. That means it will rotate 180 degrees in 12 hours, and that's half of the day. And that's what we know about the equinox, is that we have equal day and night periods. So the other thing is, let's consider the camera is facing the direction of 090. It's facing due east, and therefore the telescope, when it's level like that, is also facing due east. Now let's rotate 180 degrees and see where the telescope is facing after 12 hours. You can see it's facing directly towards the camera, so it's now facing 270 degrees. The other important thing is that at local noon, 6 hours after sunrise, it's pointing in a direction up at the sky where the sun is just passing the meridian, and at that point, if we take 90 degrees minus our latitude of 34 degrees, the angle of the telescope is going to be pointing upwards at 56 degrees. So that's the critical thing about the geometry of the equinox that cannot be explained on a flat Earth, and that is the 090 sunrise, the 270 sunset, and the angle at local noon matching 90 degrees minus the latitude. So let's have a look at some other locations. So now we have the equatorial mount set up as if it were on the equator, and that means the polar axis is horizontal like that. Now, as you can see, when the telescope is horizontal, it is still pointing directly away from us, 090 degrees. If we take 180 degrees of rotation, 12 hours, it's going to be now pointing directly towards us. So there's the 270 degrees. 6 hours after sunrise, halfway through the day, the telescope is pointing straight up. So we have 90 degrees minus the latitude, which is 0, gives us the telescope angle, which is 90. So at the equator, that's where the telescope will be pointing at midday. And the important thing to know is that this mount is only rotating in one axis all day, and it is able to track the sun. Now that is impossible on any flat Earth. So now we have the mount set up as if we were at 45 degrees south latitude. So it's angled upwards at 45 degrees. When the telescope is horizontal, it is pointing directly away from us, 090. 180 degrees of rotation later, it is pointing directly towards us, so that would be 270. And halfway, 6 hours after sunrise, it is pointing towards the meridian. Now, because of the 45-degree alignment, remember we take 90 degrees minus the latitude, which is 45 degrees, gives us our telescope angle, which in this case is 45 degrees. And again, just emphasizing that the mount is only moving in a single axis of rotation. And just to clarify, that is completely impossible to track a sun that was doing circles above a flat Earth using a single axis of rotation. There's only one place that an equatorial mount would work on a flat Earth, and that is directly at the North Pole. It would not work at any other location. But in reality, these equatorial mounts work perfectly all over the Earth, and that is why they prove that the Earth cannot be flat. So now I have the equatorial mount set up for south 75 degrees latitude. You can see it's quite a steep angle there. When the telescope is facing away from us, 090 degrees, that's the sunrise. Let's go 12 hours of rotation, and it is now pointing directly towards us. So even at the high latitude of 75 degrees south latitude, we still have that 090 270 degree sunrise and sunset. At local noon, we take 90 minus the latitude of 75 degrees, gives us the telescope angle of 75 degrees. And again, one axis of rotation. I can't emphasize that enough. It's tracking the sun with one axis of rotation, impossible on a flat Earth with the sun doing circles above. And the final position would be at the South Pole, where we would have the equatorial mount oriented like that, facing straight up. Now, we don't really have a 090 sunrise and a 270 degree sunset at the South Pole, but what happens is during the course of 24 hours, the telescope is following the sun by doing that. After 12 hours, if it was originally facing away from us, it is now facing directly towards us. And you can see that if we take the latitude of 90 degrees away from 90, that equals 0. And that is the angle that the telescope is showing.